Imagine you have 1 week to launch PulseBoard, a community app where people post short updates and follow topics. On launch morning, a creator shares one link and traffic jumps 100 times. The team opens a dashboard, sees green servers, and still gets angry messages. Posts disappear, feeds feel stale, and login works only sometimes. The mistake began before the outage. They started by drawing boxes instead of defining the user journey. System design is the practice of making trade-offs explicit so a user can complete an important action at a useful speed, even when demand, failure, and change arrive together. Start with the smallest useful contract. For PulseBoard, a member signs in, creates a post, opens a personalized feed, and receives a notification when another member replies. Write the success condition in plain language. A post should be durable before the app confirms it. The author should see it immediately. Most followers can see it within a few seconds. A notification can arrive later. Notice that these are different promises. They should not all use the same path, storage rule, or reliability target. Ask what can be delayed, what must never be lost, and what the user notices first. Next, estimate orders of magnitude. Suppose launch day has 50,000 active readers, 5,000 writers, and a peak of 2,000 feed reads each second. Suppose posts average 2 kilobytes before images. These are not forecasts carved in stone. They are working assumptions that let you compare designs. 2,000 reads per second makes a single process less comfortable. A write rate that is much lower than the read rate suggests different optimizations for publishing and reading. If the team cannot state its assumptions, it cannot explain why it chose replication, a cache, or a queue later. The first PulseBoard design is deliberately boring. A browser calls one application service. That service validates the request and stores posts in one relational database. Images go to object storage. This single-server mental model is valuable because it shows the path every request travels. It also exposes where a failure lies. If the application process stops, everything stops. If the database slows down, the feed slows down. If image delivery competes with publishing, users feel both problems. Do not call this design bad. Call it the baseline you will improve only when an observed requirement demands it. In the safe local simulation, synthetic readers request the same feed while synthetic writers publish a post every few seconds. The dashboard shows request rate, P95 latency, database connections, and error count. At 500 reads per second, the page is responsive. At 2000, the database connection pool fills and P95 latency rises. Nothing has been attacked. Nothing outside the local simulation is touched. We have simply made demand visible. The correct first response is not to add every scaling pattern. It is to identify the constrained resource, confirm the measurement, and decide whether caching, connection management, or a different data path addresses the user promise. Now draw the diagram, but draw it as a question rather than decoration. Mark the client, edge, application, database, cache, queue, and object store. Mark trust boundaries where identity or data crosses from one context to another. Mark owners for each component and its failure response. A database is not just a cylinder. It has a write contract, a replication lag, backups, permissions, and an operational owner. This habit makes a design review more useful. Instead of asking whether a diagram looks modern, reviewers can ask what happens when one dependency is slow, unavailable, or inconsistent. For this episode, PulseBoard has one decision: protect feed-read latency without weakening durable post-creation. The initial design keeps writes synchronous to the database. It treats feed delivery as a read path that may use a cache later. The team records the target, the current measurement, the capacity assumption, and the rollback plan. That is system design in miniature. Requirements lead to numbers. Numbers reveal a constraint. The constraint leads to one intentional change. In the next episode, we turn this journey into an API and data model that can evolve without breaking clients.